So, today we will talk about spin angular momentum. We have talked about the angular momentum in general, but however, for our purpose the discussion on spin angular momentum is required, and we will also talk about the total angular momentum, their algebra, the commutation relations and various things that are related to this. We have already learned that the generators of rotations are the angular momentum. So, a system having a rotational symmetry, that is, it is invariant under rotational transformation in space, has its angular momentum conserved, and the corresponding quantum numbers are good quantum numbers for the problem. So, let us look at the spin angular momentum. So, all the elementary particles that we know, they possess an internal degree of freedom, which behaves as angular momentum and termed as the spin or the spin angular momentum S. The commutation relations are written as S cross S equal to I H cross S. This is the commutation relation in shorthand notation. This, if you break it up into components, it will look like the commutation of S x S y equal to I H cross S z. S y S z equal to I h cross S x and S z S x equal to I h cross S y, and it is a cyclic permutation of that. So, it in a very compact fashion it can be written as the commutator of S I S j, where I and j are components of the spin angular momentum, is equal to I h cross and epsilon I j k S k. Epsilon I j k is called as a Levi-Civita tensor, or it is also called as a Levi-Civita symbol, which has a value equal to 1 on cyclic reshuffle of indices, and it has a value minus 1 on non-cyclic reshuffle of indices, and it is equal to 0 on having more than one index being identical. So, if you have I k, that will be equal to 0, which means equal to that. If we want to take the commutation between S x S x, that will be 0 for obvious reasons. And if you break the cyclic symmetry, that is, if you write it as instead of I j k, you write it as j I k, then it will pick up a minus sign. So, similar to this orbital angular momentum which we have learned, we can also choose this S square, which is equal to the sum of the squares of its individual components, and S z, just like L square and L z, they are the two preferred operators, and we can write down the angular momentum, spin angular momentum, in a representation in which it is diagonal in S z and S square. And of course, S square commutes with any of the components of the angular momentum, S square and S z, that is equal to 0. So, they have common eigenfunctions, and let us write the common eigenfunctions as chi of S and m s. So, these are the two quantum numbers that describe the problem of spin or spin angular momentum. S is so, they are defined in the following fashion. So, the eigenvalue of S square acting on chi S m s is equal to S into S plus 1 h cross square, and returns back the eigenfunction, and similarly S z acting on the eigenfunction will give us m s h cross and a ket chi S m s. These relations are very similar to the orbital angular momentum that we have seen, excepting that there we had written it as L and m l. However, one thing that you need to note is that there are no dependence on the space coordinates for this chi, while the angular momentum, the eigenfunctions of the angular momentum, they are the YLM functions or the spherical harmonics, which depend upon the angular variables theta and phi. These are simply numbers, or so they are simply quantum numbers which denote the eigenfunctions of S square and S z. So, there are of course other differences as well, because L and m l both were integers like 0, 1, 2 etcetera. However, for S, these are integer for bosons such as 0, 1, 2, etc., and half integers such as half, 3 half, 5 half, etc., for fermions. So, where L and ML are necessarily integers, these could be integers or maybe half integers for namely for bosons and fermions respectively. And of course, MS as earlier will have values which are minus S to minus S plus 1 through 0 to S minus 1 and S. So, there are 2 S plus 1 distinct values of MS exactly like that we have for ML, the orbital angular momentum. So, in many aspects they are similar, the algebra is very similar. However, we still need to go through some of the algebra in order to make ourselves familiar and comfortable with this this analysis of the spin angular momentum. The orthonormality condition of the eigenfunctions is written as this S prime M S prime and chi S M S is equal to chi S S prime and M S prime, which means that both the indices have to be same in order to give 1. And if any of the indices either S or MS, if they are different, then that gives a 0 because of the orthonormality relation. And the basis of S square and the component of S, that is S x, S y, S z. However, as we have said that it is only S z that is important. All these operators have a dimension 2 s cross 1 into 2 s cross 1 because of the MS value taking values, MS taking values from minus s to plus s through 0. So, there are this is the size of the vector space for each one of the components of S or the S square. And let us write down the for spin S equal to 1, and maybe we shall look at this in a tutorial for proofs. So, these are borrowed from relationships for L, and S plus which is a spin raising operator, it has the matrix elements of that between S prime, M S prime and S M S states are given by this H cross root over S into S plus 1 minus M S into M S plus 1 delta S S prime and delta M S prime M S plus 1. So, this is an off diagonal operate, or rather these are the off diagonal matrix elements, and it is very easy to understand that they cannot be diagonal, because if they are diagonal, then S M S would have been an eigenfunction of S plus or S minus, which it is not, because we are writing S plus is, as we have seen earlier, that for L plus and L minus they are written in terms of the linear combinations of S x and S y in this particular fashion, and neither S x nor S y are have eigenfunctions. SMS are not I mean SMS, none of the SMS are eigenfunctions of this S x and S y, hence they are not eigenfunctions of S plus and S minus, and hence we will have off diagonal terms in the matrix elements as it is given by this. Similarly, for the S prime S minus, which is a spin lowering operator, that has a change in this term where it is MS plus 1, whereas it is MS minus 1 and so on. So, this also connects the MS prime to MS minus 1, the later one. All right. So, let us look at some of the spin operators in the matrix form. So, that all these things that we have just seen, the matrix element written in terms of indices, general indices, can be verified. So, we are writing it for S equal to 1. Because S equal to 1, we have a 2 s plus 1 into 2 s plus 1, that is the size of the matrix. So, S equal to 1 means it's 2 s plus 1 is 3. So, we have a 3 cross 3 matrix, as you can see here. So, S x is equal to H cross by root 2, and 0 1 0 1 0 1 and 0 1 0, and similarly Sy has got a similar form with a it's of course imaginary because of this relationships that we have seen. It's 0 minus y minus I 0 and I 0 minus I and 0 I 0, whereas Sz, as we know, it has to be diagonal. So, it is equal to 1 0 minus 1 as the diagonal entries, all the off diagonal entries are 0. And similarly, the S square is also diagonal in the SMS basis. So, and this is equal to 1 0 0 1 1 1 0 and 1 0 0 1. And if you want to know, I will show it for one particular. So, these are the SMS values that you need to write down. So, S is equal to of course 1 and MS is equal to 1. So, this is SMS. So, this is like writing like a conjugate, and it is a S this, and then this is equal to 1 1 minus 1, and I will write it the ket of that, it is 1 1 and 1 0 and 1 minus 1. And if you take the matrix elements according to this relations that we have seen here, then of course, you will get this all these things. And if we so the corresponding spin eigenvectors for say Sz is given by it's a 1 0 0. So, these are for Sz, and this is equal to 1 0 0 0 1 0, and it is a 0 0 minus 1. So, this is actually same for everything, or rather it is for Sz. You can check for others what are the spin eigenvectors. First calculate the eigenvalues and then put them into the equation to calculate the eigenvectors. All right. So, let us go to the special case of S equal to half, which is of interest because we usually talk about fermions which have the spin angular momentum having a value half. So, the eigenfunctions are chi half half and chi half minus half, because these are for S equal to half we can have the MS values equal to plus half and minus half. So, of course, here again the dimension of the vector space, as we have seen earlier, it is equal to 2s plus 1 cross 2s plus 1, and for S equal to half it is equal to 2 cross 2. Okay. And these are the two eigenfunctions, calling it as alpha and beta. So, S square acting on alpha, which is half half, is half into half plus 1 h cross square, which is 3 by 4 h cross square alpha. S square acting on beta is 3 by 4 h cross square beta, and Sz acting on alpha will give h cross by 2 alpha. Sz acting on beta will give minus h cross by 2 beta. Again, remember that alpha and beta are only eigenfunctions of S square and Sz. They are not eigenfunctions of Sx, Sy or S plus S minus. Now, of course, this is a maximally aligned state, because if S is equal to half, Ms, the maximum value of Ms is equal to half. So, alpha is called as a maximally aligned state. If you operate S plus on the maximally aligned state, that will give a 0, because there is no way that you can raise the Ms value any farther, and S plus is known to raise the Ms value. Similarly, the S plus acting on beta will of course raise the Ms value from minus half to plus half. So, they will give an alpha, and of course, it will give the coefficient which is according to this relation that we have shown here. And similarly, for S minus acting on alpha will give a h cross times beta, and S minus acting on beta will give a 0, because this is a minimally aligned state, because this is equal to half and minus half. So, ms value, the minimum value of ms is equal to minus half. So, you cannot have anything lower than that. So, if S minus, which is a spin lowering operator acting on a state which has ms equal to minus half, then of course, it will be it will give 0. And similarly, you can work out, this is something very simple for you to work out, it is S x acting on alpha will give a h cross by 2 beta, S x acting on beta will give a h cross by 2 alpha, and S y acting on alpha will give I h cross by 2 beta, and S y acting on beta will give a minus I h cross by 2 alpha. S z acting on alpha will give h cross by 2 alpha, S z acting on beta will give minus h cross by 2 beta. So, you remember that once again repeating the same statement is that alpha and beta are eigenstates of S square and S z, but not of S x and S y, and that is why these two relations adequately make it clear that that they are not eigenfunctions, because S x acting on alpha does not return alpha, but it returns beta. So, let us now define a set of matrices which are quite important in the study of quantum mechanics and condensed matter physics and every other subject that we come across. These are called as a Pauli spin matrices, which are simply related to the S matrix that we have just studied by a factor 2 by h cross. So, if I multiply the spin operators that we have just learned for spin equal to half by a 2 by h cross, or write S as h cross by 2 and sigma. So, these sigmas are called as a Pauli matrices. In fact, there is let me write down that. So, sigma x, which is the x component of the Pauli matrix, sigma y, sigma z, and a 2 by 2 identity matrix can represent any 2 by 2 matrix as a linear combination. And this can be proved. Let me tell this statement a little more clearly, so that you are comfortable with this. So, let us take any 2 by 2 matrix such as A, B, C, D, where A, B, C, D are arbitrary numbers, and this is equal to some alpha sigma x plus a beta sigma y plus a gamma sigma z plus a delta I by suitable choices of alpha, beta, gamma and delta. So, alpha, beta, gamma and delta are simply coefficients. Okay. So, what about the commutation relations of sigma x and sigma y? Sigma x and sigma y have the commutation relations, which is 2 I sigma x sigma y commutator equal to 2 I sigma z, and similarly y z is 2 I sigma x, sigma z sigma x is 2 I sigma y, and which is basically again that one can write it using the Levi-Civita symbol, that is sigma I sigma j equal to 2 I epsilon I j k sigma k. Okay. So, they also have an anti-commutation relation, which are often very important, that is sigma I sigma j anti-commutator, which is written as the commutator is written with a minus sign in between the two terms, whereas this is written with a plus sign. It is a sigma I sigma j plus a sigma j sigma I equal to 2 delta I j, where I j's belong to the x, y, z components which are shown here, and we can write down the sigma x as 0 1 1 0, sigma y as 0 minus I 0, sigma z is 1 0 0 minus 1. See again we are interested in the basis or a representation in which sigma z is diagonal and it is shown as diagonal. A very interesting similarity between these three matrices, they are all traceless, that is the sum of the diagonal elements are 0. So, it is 0 plus 0 and it is 0 plus 0 and it is 1 plus minus 1. So, they are traceless, that is why they are called traceless, and the determinant you calculate that is equal to 1, which is which is equal to minus 1 and of course, as I said that in this representation all the sigma z is diagonal and the all of sigma x, sigma y and sigma z have eigenvalues plus 1 and minus 1. Okay. So, little bit of algebra if you do, it reveals that the eigenvectors are for sigma x are written as a 1 1 and 1 minus 1 corresponding to this eigenvalue, that is here lambda equal to plus 1 and lambda equal to minus 1 respectively. Sigma y equal to 1 I and 1 minus I corresponding to lambda equal to 1 and lambda equal to minus 1, and sigma z has two eigenvectors corresponding to lambda equal to 1 and lambda equal to minus 1 as 1 0 0 1 respectively. It may be given as an exercise maybe in the tutorial that for any two arbitrary vectors a and b, it can be proved that a sigma dot a, that sigma is the sigma x x cap, sigma y y cap. So, this is let me write this here. So, sigma equal to sigma x x cap plus sigma y y cap plus a sigma z z cap, and of course, a has this components a x x cap, a y y cap and a z z cap. It can be written as sigma dot a multiplied by sigma dot b, which is equal to a dot b and I sigma dot a cross b. Now, move on to the total angular momentum. Now, this total angular momentum is important in a context that I will not immediately discuss, but wherever there is a spin orbit coupling of the form L dot S, neither L nor S are good quantum numbers for the reason that L dot x can be written as L x S x plus L y S y and L z S z. Thus, since each of these individual components do not commute, neither L nor S will remain as good quantum numbers, but luckily J, which is a vector sum of L plus S, that remains as a good quantum number, and again the commutation relations are written as J cross J equal to I h cross J, J square J m J. Now, I am changing my symbol from S m S to J m J, which is equal to J into J plus 1 h cross square J m J. Same relations excepting that for L we have written it as L m L, for S we have written it as S m S, these are quantum numbers, and for J we are writing it as J m J. So, J square acting on J m J is will give you a J into J plus 1 h cross square and returns back the state J m J, and the J z acting on J m J will give a m J h cross J m J. So, m J takes values 2 j plus 1 values minus j to j, and again the matrix dimensions as earlier is that it is 2 j plus 1 into 2 j plus 1. So, as I said earlier that neither L nor S remain a good quantum number in the spin orbit in presence of a spin orbit coupling. So, J is a good quantum number, and the eigenfunctions of such a Hamiltonian can be represented in terms of J m J. Now, we are going to talk about addition of angular momentum, and very importantly something called as the Clebsch Gordon coefficients. These are quite important in various branches of physics, mainly quantum mechanics and atomic and molecular physics, etc., in even nuclear physics. So, having a good understanding of Clebsch Gordan coefficients is quite helpful. Let us see what they are, but before that let us do a little bit of algebra to familiarize ourselves with the J vector. Now, we are talking about two electrons with their total angular momentum as J 1 and J 2. So, the total angular momentum is equal to J 1 plus J 2. So, which is here. So, this is the total angular momentum. All components of J 1 and commute with all other components of J 2. Okay. So, they have all components commuting, and let the eigenstates for each one of them be taken as J 1 M J 1 and J 2 M J 2. So, just we wish to discard this J index or suffix with M. So, we simply write it as J 1 M 1 and J 2 M 2, just a shorthand notation for that, they mean the same thing. So, now we can construct product states from individual particle states. So, it is a J 1 M 1 and J 2 M 2, which are products of J 1 M 1 and J 2 M 2, just what we said, but we will write them as just like within a single ket. The product states of course have dimensions 2 j plus 1 into 2 j 1 plus 1 multiplied by 2 j 2 plus 1 and then 2 j 1 plus 1 multiplied by 2 j 2 plus 1. That is the size of the vector space, and obviously, the j 1 square will act on only j 1 m 1 and not on j 2 m 2, will give us a j 1 plus 1 j 1 into j 1 plus 1 h cross square j 1 m 1, and similarly j 1 z will give a j 1 m 1 and acting on j 1 m 1 will give m 1 h cross j 1 m 1, and similarly you can just simply change the index or the suffix from subscript from 1 to 2 and can write it for the particle 2, the same relationships will hold. All right. Now, let us work out the operations of the total angular momentum operator j square and j z, which are for the composite system, the square of the total angular momentum and so of course, there will not be any vector on j z, it is simply j z. Okay, no vector on that, on the product states. So, j z acting on j 1 m 1 j 2 m 2 will give me j z can be written as j 1 z plus j 2 z, they will act on each one of those, and so it is m 1 plus m 2 h cross j 1 m 1 j 2 m 2. The simultaneous eigenfunctions of j 1 square, j 2 square, j 1 z and j 2 z are also eigenfunctions of j z. So, at least one thing we have been able to settle is that for the total the z component of the total angular momentum, that is j z, has same eigenfunctions as each one of those j 1 square, j 2 square, j 1 z and j 2 z. But what about j square? What are the eigenfunctions? Do they have the same eigenfunctions as j 1 square, j 2 square, j 1 z and j 2 z? J square is written as j 1 plus j 2 whole square, and it is written as j 1 square plus j 2 square and j 1 j 2 plus a j 2 j 1. Now, since every component of j 1 commutes with every other component of j 2, we can combine this to write as 2 j 1 j 2. So, the j square contains a twice of j 1 dot j 2. Now, j 1 dot j 2 is j 1 x j 2 x plus j 1 y j 2 y plus a j 1 z j 2 z. Now, since the j 1 x and y, they do not commute with j 1 z. So, j square as it contains j 1 dot j 2 does not commute with j 1 z dot j 2 z. Okay. So, this is a very important result, because we just found that Jz commutes with J1 square, J2 square, J1z and J2z. However, J2 I mean the whole J square does not commute with these. So, thus the simultaneous eigenfunctions of J square and Jz are eigenfunctions of J1 square and J2 square, but not J1z and J2z. Even though Jz has same eigenfunctions as J1z and J2z, but J square does not have. So, thus there exist two distinct descriptions of the system in terms of the eigenfunctions of J1 square, J2 square, J square and Jz, and J1 square, J2 square, J1z and J2z. Okay. Now, this is important because if there are two such identical descriptions of a system, then there has to be a unitary transformation or a relation that connects these two bases. So, the eigenvalues corresponding to 1 is this, let us call this as 1 and this as 2, it is written there of course, on the left hand side, and this is equal to J1 into J1 plus 1 h cross square and J2 into J2 plus 1 h cross square and J into J plus 1 h cross square and m h cross, as the eigenvalues corresponding to 2, which are these J1 square, J2 square, J1z and J2z are J1 into J1 plus 1 h cross square and J2 into J2 plus 1 h cross square and m1 h cross and m2 h cross. So, the eigenfunctions corresponding to 1 are J1, J2, Jm, and the eigenfunctions corresponding to 2 are J1, J2, m1 and m2. Since both define the complete vector space, there has to be a unitary transformation connecting the two bases. The coefficient of the unitary transformation are known as the Clebsch gordan coefficients, which we intend to compute for a given case. So, once again, both define a complete vector space for a problem of J square and Jz. So, now there has to be a unitary transformation connecting the unitary transformation that connects the two bases, the coefficients corresponding to that are called as the Clebsch gordan coefficients. So, we are writing these states as J1, J2, Jm and the J1, J2, m1, m2, and now the coefficients are the overlap of these J1, J2, m1, m2 and J1, J2, Jm. The restriction on the sum is that m2 has to be, there is a sum over m1 and m2. The restriction on m2 should be that it is the total m minus m1. So, we want to determine the values of j for a given j1 and j2. Okay. The values of m1 and m2 of course, range from minus j1 to plus j1 through of course 0, which we have not written here. There is a 0 here and there is a 0 here. Similarly, for m2 it is minus j2 to plus j2. Since m equal to m1 plus m2, the values of m and all the corresponding m1 values for m1 and m2 can now be assigned. Let us look at the table. For m to be having the maximum value, which is j1 plus j2, my m1 can be j1 and m2 can be j2, and that is the only way to achieve the maximum value of m. However, when we take the next to the maximum value, that is j1 plus j2 minus 1, there are two possibilities, that is either m1 can be j1 minus 1 and m2 could be j2, and also m1 can be j1 and m2 can be j2 minus 1. So, these are the two possibilities that we are showing here, and similarly for the third one, that is the next to the is j1 plus j2 minus 2. So, there is a j1 minus 2 and j1 minus 1 and a j1 and it is j2 and j2 minus 1 and a j2 minus 2, it is a threefold degenerate. So, we are writing down the degeneracy on the rightmost column, the first one having a degeneracy 1, the second one having a degeneracy 2, third one having a degeneracy 1, because all combinations are possible, and the lowest value of m is minus of J1 minus J2. So, each of M1 and M2 can take values minus J1 and M2 can take value minus J2, and again the degeneracy is equal to 1. So, these are the values that the total angular momentum can take for the composite system, that is m values, and vis-a-vis the m1 and m2 values, which are the individual quantum numbers for the total angular momentum they can take. All right. So, now still that question which we have posed earlier remains, that is how to figure out the allowed values of j for a given value of J1 and J2. So, the maximum values of M1 and M2 are J1 and J2, such that m equal to J1 plus J2 equal to j. So, the maximum value of m is J1 plus J2. So, remember m can take only values which are from 2j plus 1 values from minus j to plus j. So, the maximum possible values of j is J1 plus J2. So, case 1, that is the top of that table that we have seen here. So, take the maximum value of j equal to J1 plus J2 and the maximum value of m, which is equal to J1 plus J2. Again, there is just one term in the sum with m1 equal to J1 and m2 equal to J2. Go back to this sum that we have shown here for the Clebsch gordan coefficients. We need to sum over m1 and m2. So, we need to know the precise values of m1 and m2 such that we can perform the sum. So, m1 equal to J1 and m2 equal to J2, and now we introduce another shorthand notation, that is J1 J2 Jm as phi J1 J2 and in the superscript Jm, and similarly for the other basis we write psi of J1 J2 m1 m2. Thus, phi which is the one of the basis which is J1 J2, and for j equal to J1 plus J2 and m equal to J1 plus J2 again, that is the which has a degeneracy equal to 1. So, there is nothing to sum up, and this is written, the Clebsch gordan coefficient is written as J1 J2 J1 J2 J1 J2 J1 plus J2 and J1 plus J2, and then the psi the other basis, and since both phi and psi are normalized, this Clebsch gordan coefficient must be equal to 1, it has to be normalized. So, this Clebsch gordan coefficient equal to 1. Let us now take the same j, which is J1 plus J2, but take the next lower value of m, which is J1 plus J2 minus 1. This is the term in the second term in the table that we have just shown. So, in this particular case, this has two possibilities, namely you see here that is a J1 minus 1 and a J2, and also a J1 and a J2 minus 1 for M1 M2. Thus, phi J1 J2 and J1 J1 plus J2 minus 1. So, this is equal to this should be equal to J1 plus J2. Should be linear combination of two linearly independent eigenfunctions, namely psi J1 J2 J1 J2 minus 1 and psi J1 J2 J1 minus 1 and J2. Moreover, two such linear combinations are appearing, one for j equal to J1 plus J2 and the other for m equal to j plus J2 J1 plus J2 minus 1. Proceeding further to the next one, m equal to J1 plus J2 minus 2. So, we shall have three linearly independent sets for values of m1 and m2, which are J1 minus 2 J2, J1 minus 1 J2 minus 1 and J1 and J2 minus 2 and so on. So, this will go on. Let us take a simple example to calculate the Clebsch gordan coefficient. Now, this is quite a task to do it for a complicated problem, and which we want to avoid here, but we will still the essence still remains the same, and we will show it for a particular case. So, once again to remind you that we will write down the kets as this, where C m1 m2 are the CG coefficients. Let us have, so you have to calculate C m1 m2 for J1 J2 Jm as 1 1 1 and minus 1, that is j 1 equal to 1, j 2 equal to 1, j equal to 1 and m equal to minus 1. So, since total m is equal to minus 1, m 1 plus m 2 must be equal to minus 1. So, either m 1 equal to minus 1, m 2 equal to 0 or m 1 equal to 0 and m 2 equal to minus 1. So, I can write down this as C 0 minus 1 and 1 0, and this is for the first particle, and this 1 minus 1 is for the second particle. This is the shorthand notation for 1 1 0 minus 1, and similarly, it is a C minus 1 0 1 minus 1 and a 1 0 ket, which is a 1 1 minus 1 0. Now, in order to calculate this, a trick is required, that is, if we since this is a minimally aligned state, that is m has the value which is minus 1, if we apply a j minus 1, because your j is equal to 1. So, m is the minimal value of m is minus 1. If we apply j minus on the state, it will give me 0. So, j minus is simply nothing but j 1 plus j 1 minus plus j 2 minus, which will act on this state and will give me 0. So, that will use those relations that we have learned earlier, that is j plus minus acting on j 1 m 1 is equal to j 1 plus 1 and a minus m 1 and m 1 plus 1 or minus 1, depending on whether you are applying the raising operator or the lowering operator. Here we are interested in the lowering operator. So, that gives a state which is 1 1 minus 1 minus 1, and because this is equal to 0, these kets are not equal to 0 and neither root 2 is. So, we have this bracket equal to 0. So, if this is equal to 0, then we have a C 0 minus 1 equal to minus of C minus 1 0, and so each one of them, if you normalize it, becomes equal to 1 over root 2. This is of course, one is 1 over root 2, the other one is minus 1 over root 2. So, this is the way we have calculated the Clebsch Gordan coefficient for this state given by here. All right. Let us go through some of the problems which you may see in the tutorial, and these are exercise problems. Nevertheless, it is important for me to just browse through them, which are the relations that you need. There are some commutation relations which you have seen in some form. I am writing them down again. It is a commutation between L plus L minus, which gives a 2 h cross Lz, and Lz and L plus minus gives a plus minus h cross and L plus minus, and similarly L square and L plus minus commutator always gives 0, because L plus minus is nothing but a linear combination of Lx and Ly, and because L square commutes with all components of L, that is why this is equal to 0. And similarly, for the spin angular momentum, sigma I sigma j equal to 2 I epsilon I j k sigma k, and sigma I sigma j, the anti commutator is equal to 2 delta I j. So, these are the problems that you should do and practice in order to have familiarity with the angular momentum algebra. So, L plus minus acting on L ml equal to we may not write this ml, but since we have written, let me just add that ml here. L plus minus acting on L ml is h cross root over L into L plus 1 minus ml into ml plus 1, and L ml plus minus 1. Of course, as I said earlier, that these are not the eigenfunction. So, one gets a different state after one operates L plus minus on L ml. And let us say find the eigenvalues and eigenfunctions of a spin half particle pointing arbitrary direction in space. So, we have now so far talked about z being the preferred direction, in which case Sz has always been diagonal. Suppose the spin vector is pointing in some particular direction in space, which is the n cap direction, then what are the so these are the, so this is phi and this is theta, or so this is theta and so on. And so this can be worked out, and you can find out the forms for the Pauli matrices, which you have learnt. Look at this problem, that write down the matrices corresponding to Lx, Ly and Lz for L equal to 2. So, L equal to 2, the size is equal to 2L plus 1 cross 2L plus 1, and this is equal to 5 cross 5. So, we will have a 5 by 5 matrix, which are written as Lx is equal to h cross by 2, and these all these elements that are written there, Ly equal to h cross by 2 and all these elements. Lz of course is diagonal. When you have L equal to 2, the ML values are 2, 1, 0, minus 1 and minus 2. So, these are appearing at the diagonal entries, and all the off diagonal entries are 0. Of course, this is the eigenstate of Lz. The basis is an eigenbasis of Lz. Let us do a problem which is a two dimensional rotation operator. You have looked at the rotation operator in 3 dimension, which you know that if you rotate a system or an object about the z axis, then what the rotation matrix is. We are simply talking about a rotation in the xy plane, which has a form which is written here. For this u r of theta, so show the group property. So, basically u r forms a group, and there are elements of the group and they have certain properties. So, these is one group property, which is u r theta 1 and u r of theta 2, which is u r theta 1 plus theta 2. And so, this is called as the associative property. So, u r of theta is written as cos theta sin theta minus sin theta cos theta. So, u r of theta 1 into multiplied by u r of theta 2 is the product of these two matrices, and this is equal to, if you do the simplification, it comes out as this, and this is equal to u r of theta 1 plus theta 2. So, that property can easily be proved, and so we stop here with having told you most of the relevant things that are needed for the angular momentum, including its commutation relations, the algebra that is needed, and various things such as it being the generator of rotation. And the reason that the rotation operators do not commute, because the components of the angular momentum do not commute, and in general when you write it as matrices, one should understand easily that they do not commute, because matrices do not, matrix multiplication is non-commutative in general.